Welcome, everyone. Today we're getting into a classic coding challenge, often called the two-sum problem. It seems simple on the surface, but how you actually solve it really matters for performance.
It really does. The basic task is you get a list of numbers, say 2, 7, 11, 15, and a target number, maybe 9.
Okay.
Your job is to find two numbers in that list that add up exactly to that target, 9. And you don't just find the numbers, you need to return their positions, their original indices.
Right. So for that 2, 7, 11, 15 list and target 9, it would be 2 and 7.
Exactly. And they're at index 0 and index 1. So the answer you'd give back is 0, 1.
Got it. And like you said, sounds straightforward, but the way you find that 0, 1 makes a huge difference, especially if that list gets really, really long.
That's the core of it. We're going to look at a Python solution that uses something called a hash map, a dictionary in Python, and see why it's so incredibly fast.
And this gets us into some really practical programming ideas, doesn't it? Like time complexity.
Absolutely. We'll be talking about time complexity using Big O notation. It's fundamental to understanding why this hash map approach is so much better than just, trying every single pair.
Okay, let's unpack that efficient Python code then. The key thing seems to be this nummap you mentioned, the dictionary.
That's right. We start by creating an empty dictionary. Nummap. This is going to be our lookup tool.
And then you go through the input list, the nums.
Yep, we loop through it. A neat way in Python is using enumerate. So for I, num in enumerate, nums. This gives us both the index, I, and the number, num, in one go.
Which is handy because we need both the number and its original position, the index.
Exactly. So for each number num we encounter in the loop, we calculate what we need to find. The complement.
The complement being just the target minus the current number.
Precisely. Complement target num. This is the other number we're looking for to make the pair.
Okay, so you have the current number num, and you know the complement you need. Now what?
Now comes the clever part with a hash map, our num map. We immediately check, is this complement already a key in our num map?
Ah, so you're checking if you've already seen the number that would complete the pair.
Yes. If complement in num map, it means we found it. We found the second number. The dictionary num map stores the numbers we've seen and their indices.
So if the complement is in the map, you just return the index stored for that complement, which you get from nummap complement, and the index I of the current number num.
Bingo. You return nummap complement, IJOM, instantly.
And what if the complement isn't in the map yet?
Good question. If it's not there, it means we haven't found the pair yet with this number. So we take the current number, num, and its index, I, and we store them in the num map.
You add it for later.
Exactly. Num map num equals I. So the next time we loop, if that number happens to be the complement someone else is looking for, it'll be there waiting in the map.
Okay, that makes sense. You're building up this map of seen numbers and their locations as you go.
Right. And the crucial performance gain comes from how fast that check is.
Yeah.
Complement in nummap. Checking if a key exists in a Python dictionary, our hash map, is on average incredibly fast.
That's the big O of 1 thing, right? Constant time. Doesn't matter how big the dictionary gets, the lookup time stays roughly the same.
Exactly. Big O of 1 on average. Compare that to the simple brute force way, where you just use two loops.
Yeah, nested loops. Check the first number against the second, then the third, then the fourth, then check the second number against the third, the fourth.
Right. You check every single possible pair. That approach works, but its time complexity is big O of n squared.
N squared. Meaning if the list size doubles, the time potentially quadruples. Ouch.
Big ouch, especially for large data sets. But this hash map solution, we only go through the list once.
So it's linear, big O of n. If the list doubles, the time roughly doubles. Much, much better.
A massive difference. It can be the difference between seconds and, potentially hours or even days for really huge inputs.
Now, there is a trade-off, isn't there? Space.
Good point, yes. The hash map solution uses extra memory. In the worst case, we might store almost every number from the input list in our nummap. So the space complexity is big O of n.
So linear space usage. You trade memory for speed.
Which is often a very worthwhile trade-off in modern computing. Speed is frequently the bottleneck.
So stepping back, this two-sum pattern, it's not just an abstract puzzle, is it? Where might you actually see this kind of logic used?
Oh, it pops up in various forms. Think about finding two items in an online store that add up exactly to a gift card amount.
Or maybe combining time durations, like finding two tasks whose times add up to a specific meeting slot.
Yeah, or even in data analysis, like finding pairs of sensor readings that sum to a certain threshold, or maybe grouping student scores on different assignments to see who hit a target total. It's surprisingly versatile.
It really highlights how picking the right tool, in this case, the hash map or dictionary, can completely change the game for efficiency.
Absolutely. It's about understanding your data structures and algorithms. That dictionary lookup is the key to avoiding that costly big O of n squared brute force approach.
So for you listening, think about the data you work with. Are there situations where you need to find pairs or combinations that meet a specific condition, like summing to a target?
Could using a hash map, like this num map, help you speed things up? It's worth considering how these fundamental ideas might optimize something you're working on.
A really neat example of how a smart algorithm makes a world of difference. Thanks for unpacking that.
My pleasure. It's a great illustration of core computer science concepts.